Hello everyone, in this e-course we will discuss about the demand and traffic forecasting modules, the hybrid intelligence approach for traffic forecasting, as well as the auto-calibration framework for traffic simulation that were developed for ACUMEN project. I am Panagiotis Fafoutellis, a postdoctoral researcher at the National Technical University of Athens, and with my colleagues from the University of Luxembourg and UG, we have prepared this presentation. Let's start with the demand estimation. The main activities of this task were demand estimation and forecasting, and in particular the development of model and data-driven approaches for predicting the demand both at the level of trips and at the level of infrastructure utilization, so that this information could be provided as input to different traffic management solutions. One of the main advantages of the demand estimation and forecasting approaches developed in ACUMEN is the use of the different types of data that has been collected. So the work done is broadly divided into 4 elements. First, modeling spatiotemporal patterns. This part is innovative in the sense that it combines classical utility theory and activity travel behavior principle with more novel data-driven methods based on advanced statistics and machine learning approaches. This allows to create spatiotemporal patterns which are consistent and emerging from individual choice processes that reflect the observed trips, allowing then a reliable estimation and prediction. The data-driven techniques, on the other hand, are based on novel Gaussian processes and machine learning techniques and allow to have both mid-term predictions, so forecasting of tomorrow patterns, or shorter term, such as next hour demand predictions. The models have been tested on synthetic data that has been collected from Luxembourg, and this synthetic data has been used as a benchmark dataset to quantify the accuracy of the modeling approaches and the estimation and predictions. The application has been done on forecasting the park and ride demand for the city of Amsterdam within the pilot of Amsterdam. This slide shows the methodological framework of the data and the demand forecasting tool developed within ACUMEN. In particular, it shows how the ACUMEN data lake provides input to the demand forecasting techniques as well as the traffic forecasting task. Then, the demand forecasting provides as a result the different predictions, and these predictions are fed back into the data lake and then can be also visualized in the ACUMEN Data Digital Twin platform. And then the estimation and prediction of the trips and the spatiotemporal demand patterns are also input for the different door-to-door traffic management strategies. So the Amsterdam pilot will be an example, but all what has been developed can be used to reconstruct trips, to predict trips at different modes of transport, and then be utilized for different types of management scenarios. Going more on detail on the different elements that are the basis of the demand estimation and prediction, let's start with the spatiotemporal pattern modeling. As already mentioned, this is based on a utility maximization framework where the general idea is that trips are essentially the emerging results of activity and departure time choices of people. So generation of trips is basically being reconstructed through the fact that different origin-destination travels are guided by the principle that people want to maximize their daily utility, and by doing so they perform activities at different destinations and they stay within these activities as long as the utility accumulated is higher than being elsewhere and doing other activities. Through the part of time choice model, then people choose what is the best time to start the trip in order to reach a destination where the activity is performed, and at what time the activity should be stopped and then another trip is generated to go to the next activity. This approach is then linked to demand estimation technique based on Markov chain and Monte Carlo and Bayesian updating, which allows to use observed aggregated trip data and then identify the most likely utility parameters that in turn generate the trips. By doing this to different origins and destinations, then activity-specific and mode-specific origin-destination trips can be estimated and reconstructed. And on the bottom right, one can see how time-of-day trips by different modes of transport can be reproduced and can be consistent with the observed ones, the real profiles. This allows a pure multimodal origin-destination estimation and then to have multimodal origin-destination trips to be used as input for the multimodal traffic management strategies. Next is the multimodal demand estimation and forecasting. This part considers advanced statistics techniques which are able to reconstruct the trips from the previous spatial temporal patterns which are used to sample individual trip chains. In particular, the use of multi-Gaussian processes allows to create synthetic populations from these sampled individual trip chains, and these synthetic populations are used in the ACUMEN digital twin. These synthetic populations are accurately reproducing the trip chaining of people. So for every trip sequence that individuals do, the correct activity and the mode of transport that is likely to be used can be predicted. Finally, the last step of the demand estimation and prediction is the data-driven demand prediction part. In that respect, what we did was to directly use the data and the different datasets that are collected in the ACUMEN data lake, and then through analyzing the time series of the data, especially of the different infrastructure, and through short-term estimation techniques based on machine learning approaches, in particular a combination of long short-term memory and sequence-to-sequence modeling approaches, we could then have shorter-term prediction of the state of traffic and the state of different infrastructure utilization, and in particular parking and charging. This is very important because on one end, trips for origin and destination provide to us the amount of people that we need to serve and we need to take into account during the management approaches, and on the other hand, the short-term demand and state prediction of the supply system allows to also understand what is the available capacity in the short term in order to guide the trips and redirect traffic to the infrastructure that can accommodate the extra traffic. So long short-term predictions and sequence-to-sequence approaches allow then next hour predictions. And these next hour predictions have been tested on the Amsterdam pilot. In the Amsterdam pilot, we used the information about 8 park and ride station locations, and then we performed the prediction of the occupancy of the different park and rides by time of the day. And this information is used for the scenario of the tunnel closure and the redirection of traffic to different park and rides in order to continue the journey on the public transport services. So the machine learning models previously described have been used and trained on the 8 locations and then have been tested on the 4 park and ride stations that are involved in the rerouting scenario. The picture shows how predictions can accurately identify the temporal patterns of the different stations, and in some cases, especially in the busiest locations, the accuracy of the predictions can reach up to 96%. Now we move to the short-term traffic forecasting module. Our methodology has 3 elementary aspects. First, we use Granger causality to detect causal spatiotemporal relations between the locations of the road network. Then, to increase the model's trustworthiness, we incorporate traffic flow theory aspects by following an approach that is based on the concept of physics-informed neural networks. So causality is a concept that is more generalizable than statistical correlation, which makes it very important in forecasting tasks. In simple words, the Granger causality test is a well-established method for time series data, and we say that a time series X Granger causes a time series Y when Y is more accurately predicted by a model if previous values of X are included in the input space. For the purposes of this task, we use Neural Granger, which is an innovative deep learning method based on the LSTM architecture, which is trained using the loss function presented in the slide, and assigns 0 input weights to input time series that are not causally related with the target time series. By applying this method with data of 6 minutes resolution, with data from 400 loop detectors from Athens and a look-back window of 1 hour, we were able to detect the causally related loop detectors, which lead to two main outcomes. First, that the perimeter locations Granger cause the traffic conditions at the center of the city, and secondly, that there are some detectors at significant highways that were found to Granger cause most of the rest. Next, we proceed to develop the theory-informed models which take causally related input and are based on the concepts of physics-informed neural networks and multitask learning, as they have two output variables, the traffic volume and speed. The models are trained using a novel loss function that is presented in this slide, which was designed and implemented during the project, and takes into account both the distance of the predicted pair of values from the actual pair and from the closest point of the fundamental diagram, as it can also be seen in the picture. The loss function is easy to implement and is compatible with any deep learning models. It becomes clear that the first step to implement the theory-informed models is to have a fundamental diagram for each location or for each loop detector in our case. For this task, we use a simple data-driven approach by first separating the points belonging to each branch of the fundamental diagram into two clusters and then fitting a second-order polynomial curve at each branch, as it is indicated by the values of R-squared metric and also by observing the figures. By using this method, we were able to successfully fit the fundamental diagram of each location. Based on what was presented, we trained LSTM-based theory-informed models for different locations of the road network of Athens and compared with models of the same architecture and hyperparameter values that were trained using the classic MSE loss function. For the indicative locations presented here, we see that our approach improves significantly the overall value of the mean absolute percentage error, and also by observing the emerging fundamental diagrams of the predicted traffic conditions, which are with black color, they are a lot closer to the actual, which indicates the increased trustworthiness of the proposed models. We can finally say that the main difference between the two models is that the simple MSE model fails to predict accurately the congested branch of the fundamental diagram. Next is the development of hybrid models using a human-in-the-loop approach. The objective of this task is to design a fail-safe forecasting system where a human user audits AI models in real time and intervenes based on the principles of human-in-the-loop systems when high risk for highly erroneous predictions is detected. The components of the framework are a traffic forecasting and an incident detection models, a module of the estimation of the riskiness of the situation, the human intervention framework and the corresponding action space, which includes the human's possible actions, which are in this case the selection between alternative models to perform the forecasting task. As far as it concerns the risk assessment framework, we first estimate the uncertainty of each prediction and classify the current traffic conditions using another module that was also developed in ACUMEN, and when the uncertainty exceeds a specific threshold or the current conditions correspond to unexpectedly heavy congestion, we ask the human to intervene. More specifically, we have developed a graphical user interface that acts as a bridge between the AI models and the end users. It simulates real-world data streaming, and the models are providing their predictions in real time, and when a risky situation emerges, it notifies the human to act by selecting between the predictions of two alternative models. The user's response is saved to be analyzed, and the expected outcome is an overall prediction performance improvement. The two models that are used in our framework are the theory-informed model that was presented before and the simpler random forest model that was trained exclusively on data corresponding to non-recurrent events. Both models use an input time series of the previous 30 minutes, which corresponds to 20 time steps. The participants of our experiments were experts from the academic sector as well as employees of road operators and authorities who used the human-in-the-loop interface for 72 simulated hours, observing traffic and monitoring the models, intervening when they asked. The main objective was to evaluate the effectiveness of integrating a human user into the forecasting process. The graphical interface includes a visualization of the uncertainty of the predictions of the selected model, a time series of traffic speed and volumes for the last 30 minutes, the predictions of the alternative models, and a color code based on the classification of the traffic conditions. Additionally, to support the user's decisions, we provide error and uncertainty metrics, the fundamental diagram of the corresponding location, and the visualization of the residuals of previous predictions. Here you can see a short video of how the user interface is used. Our results indicate a significant improvement of the forecasting accuracy, especially during non-recurrent congestion, which is the most challenging situation as well as the most important for successful traffic management. Finally, we can now move to the auto-calibration module. In order to develop the auto-calibration component for simulation applications, we accomplished the following objectives. First, we developed a direct calibration framework for multimodal MFDs using heterogeneous historical data by proposing robust data fusion technology for MFD models, developing spatial scaling methods to scale up from sensor-equipped networks to the full network, and identifying recurring network dynamics patterns and categorizing them to establish auto-calibrated MFDs. In addition, set the foundation for real-time indirect auto-calibration to be integrated with M&M's simulation platform for dynamic simulation adjustment, also implemented and calibrated in EMSA Next simulation software. This slide presents the data used for this task, including loop detector data from Athens Detectors Network, floating car data from the same road network provided by partner here, as well as public transport GTFS data for 65 bus lanes. Here we have the different steps for calibrating the multimodal MFD. First is to fuse loop detectors, probes, and public transport data. detectors and probe data are used to improve the spatial mean speed estimation through machine learning, while public transport data provides specific information, for example, number of vehicles on the network and actual commercial speed for the bus. Step 2 is scaling, meaning getting the full MFD over all links while observations are available at some locations only, mostly for the loop detector locations. We have developed a hierarchical scaling process that reduces the scaling bias, which usually is based on the fraction of the equipped links versus non-equipped links. But this homogeneous scaling does not account for different traffic behavior on the different parts of the network. And step 3 is longitudinal analysis that provides a recommendation on which MFD to use on which type of day, giving a full vision of the network behavior. An example of resulting multimodal MFD is also given here. Finally, we compared the state-of-the-art methods with the new ACUMEN framework for car MFD, considering different penetration rate for loop detectors, considering the usual rate of a city, which is between 5 and 10%. One can see that our hierarchical scaling approach provides much better estimation than the state-of-the-art methods when the penetration rate for loop detector is low, which is the typical operation case. The methods presented were also implemented and tested in the project's pilot experiments, and more information can be found in the project's website and the public deliverables. Thank you for watching this video.